So in this video, we're going to address the issue of channels and spatialization. Essentially, how many amplitude values do we need to record at each sample in time in order to send them out to multiple ears of headphones or multiple speakers and to simulate the location of sounds in space. So as we talk about channels and spatialization, I first want to talk about two important phenomena related to this, inter-aural delay time and the head-related transfer function. And then we'll talk about how these can combine to simulate the spatialization of sound with headphones through a process called binaural sound. And then we'll talk about what we might need to do differently if we're sending sound out over multiple speakers with sound diffusion. But first, I want to talk about inter-aural delay time and the head-related transfer function. And to do that, I need to do some drawings. And as usual, I want to apologize that I'm not the best drawer in the world, but I think that this will get the point across fairly well. So let's pretend that that circle is your head, and that's one of your ears. This is another ear. Let's say that's your nose. So you're looking kind of that direction. And then we have a sound over there. So as that sound is traveling to your ears, you can imagine that there's a sound wave kind of going that way to your right ear, sound wave going that way to your left ear. Now what's important here is that the length of those two lines that I drew is a little bit different from each other. It's going to take longer for this sound to get to your left ear than to your right ear because it has to travel just a little bit further. And so there's going to be a difference in phase between those two sound waves as they reach your two ears. And we can actually, when we're listening to sounds in the real world, we can automatically kind of process that difference in phase and use that as a cue to understand where that sound is coming from. Something else that we use as a cue, so that's called the inter-aural delay time, or the IDT. That difference in the time delay between when sound gets to your right ear and when it gets to your left ear. The other thing that we use is the HRTF, the head-related transfer function. And this simply means that if we look at this line here, you can see that this last little bit here, that sound to get to your left ear is actually traveling through your head. And so sound, depending on where it's coming from, might have to get through your head to get to your ear. It might have to get through parts of your ear, your outer ear, like this part or something like that. It might have to go through all different parts of your head in order to get to your ear and actually be heard. And as it travels through your head, that's different from it traveling through air. In particular, some of the higher frequency components of that sound are going to lose some more energy. And so it's going to sound different by the time it gets to your ear because it's had to travel through your head or through your outer ear or through all these different places. And again, we kind of automatically pick up on these cues. And this helps us to figure out where a sound is coming from. So these two things together, along with a few others, this inter-aural delay time and head-related transfer function, are really powerful cues for us to get a sense of where the sound is coming from in space. So we can take advantage of these if we're listening on headphones to do something called binaural sound. And binaural sound is essentially spatialized sound that's designed explicitly to be heard over headphones. And there's two different ways that we can create binaural sound. One is that we can use a special microphone called a binaural microphone. And here's a picture of one right here. It essentially looks like a pretend human head with pretend ears sticking on the side. And then what actually happens is there's a little microphone embedded inside of that pretend ear, and there's a little one embedded inside of that pretend ear. And so we can put this in a place when we're recording, and that's going to mimic the inter-aural delay time because those microphones are placed apart from each other, somewhat according to the placement of our ears and our heads. And also the material that it's made out of is going to mimic that head-related transfer function of the sound passing through our heads or our ears. So then if we play this back over headphones and we send what was recorded in the left ear to our left ear, send what was recorded on our right ear to our right ear, we get a very good sense of how the sounds were in space at the time that we were recording them, what was in front of us, to our left or right, behind us, and so on and so forth. The other thing that we can do, of course, is we can try to simulate these effects digitally through applying artificially that phase difference of the inter-aural delay time and some filtering of changing the frequency response to mimic that head-related transfer function to simulate a sound coming from a particular location in space. And what I have for you now, if you're listening on headphones, if you're not listening on headphones, this won't work. But I encourage you to put on headphones and look at a couple of YouTube videos that demonstrate each of these phenomenon. The first one simulates this binaural microphone. It doesn't simulate, it actually is a binaural recording. So you can see the musicians on the video, and you can hear where they're coming from through the binaural recording. And then the second one is a simulated binaural effect that was done digitally, simulating all these different sources coming from different places. So I want you to take a moment now and listen to those two examples over headphones to get a sense of how binaural sound works. So binaural sound is great if you're listening over headphones, but it doesn't work so well if we're listening over speakers. Because when we're listening over speakers, if we have, say, stereo speakers, we don't have the luxury of having only the left channel go to our left ear and only the right channel going to our right ear. We don't get that isolation. They're both going to go to both of our ears. So we can't really simulate the interaural delay time or head-related transfer function so well over speakers, where both channels are going to both ears. So if we can get some limited sense of, of spatialization with stereo, left and right. But if we want to get more serious, we need to get more speakers involved. And you all have probably heard of a 5-1 surround sound, for instance. That's the basic idea that we have in the front. We would have a left, center, and right. And then in the back, we'd have a left and a right. That's how we get our 5 channels of sound. This is what's used in movie theaters. That's what's used in home theater systems as well most of the time to try to give a basic sense of sound moving through space. And so if we have those 5 channels, we can do that. We can obviously have more channels too. It's fairly common, especially in kind of the academic world of computer music, to have 8 or 10 or even more channels of surround, where there's more and more speakers around the space to be able to simulate space a little bit more precisely. And when we do this, we have special software that can usually help us to figure out how much of each sound we want to send to each speaker. So for example, here, this is a surround mixing program from Reaper. We see that the speakers are where I drew these arrows before. There's these kind of yellow things. But then we have 3 sound sources, numbered 1, 2, and 3. And so we can drag those around in a user interface to show where we want them to sound like they're coming from. And then it'll control kind of mixing those sound sources to each of these 5 speakers differently. So it'll try to simulate those spatial effects for us. At this point, you might be wondering, if you don't know already, what the 0.1 means in the 5.1. And that's for the low frequency effects channel, or the subwoofer. So in these things, we'll have these 5 speakers that are placed spatially around the room, but we'll also have one subwoofer that is really focused on very low frequency sounds. The reason for that is that we're not as sensitive to spatial location of extremely low frequency sounds as we are of higher frequency sounds. And we need much bigger speakers to be able to really reproduce these really low frequency sounds effectively. So a 5.1 system would just have one of these giant subwoofers for producing these really low frequency effects, and then the 5 kind of regular sized speakers or clusters of regular sized speakers to give the effects of sound moving through space. One final note I wanted to make was about ambisonics and other systems like that that exist that let you specify the locations of sounds independently of whatever speaker configuration you want to use. So with ambisonics, you can specify where you want your different sound sources to be placed, and then you separately specify where your speakers are located. And then from there, it can kind of compute that all dynamically, so that you aren't tied when you're creating a piece of music to a particular speaker configuration over which it's going to be played. So to review here quickly, we talked about ways that we hear sound in space, interaural delay time, head-related transfer function. And we also talked about binaural recording and processing, which are very effective if we're working just with headphones. And then we talked about different speaker configurations available to us for diffusion of sound in space through speakers. In the next video, we'll talk about the question of how we actually take all this data and store it, how much space it takes up on our disk, and different file formats that are available to us to manage that.